I hope you interrupt me if there is anything I say that is not clear. If you have any questions? It's a bit of a challenge for me because I'm a physicist, so I'm talking to people with different backgrounds. And also I'm explaining things in a way a bit different from the why I have to prepare my slides before coming here. As you well know, I was working on this because I changed a bit my standard presentation to accommodate maybe to this audience. Let's see how things go. So if you're unhappy or I say things that are a bit weird, you should tell me because I give feedback to appreciate it. Okay, so I'm going to tell you about randomness. And so in all what I'm going to say, I will use a lot of the concept of causality. Okay, so you can, I think we may all agree that a lot of scientific activity is devoted to addressing understanding which causes can explain some observed correlation. Okay, so you make some experiment, you observe some outputs, when you make some actions in some given points in space-time, and you try to explain what would explain this correlation. No? So I think it's, if there is someone making an action X and getting an output A in a given region, say in space-time, you want to see how this will affect the actions by another observer in another location, making some actions Y and getting result B. So in my talk, I'm going to reason a lot with these devices. So this in quantum information theory, we call this device-dependent quantum information processing. But I think now we don't need, you only have to understand that I'm going to reason about systems in which you will perform actions and get some outputs. And I want to do these things in a theory-independent way. Okay, so at the moment, I'm not going to say that these are quantum particles or these are classical particles. I don't know. It's just observers making actions in some given devices and getting outputs. And well, of course, what I will consider is that we put labels to these actions, okay? And this usually the way observers reason about labels is with classical information, okay? So you can think of this as you having a device in which you can do some actions. Say you have buttons, but it can be whatever. So you can have n buttons, and you decide to press a given button. And then at the bottom of your device, you have some detectors, some lights, and by you pressing a button, one of the lights is on. Actions, but it can be any action. Okay, so it can be you put a knob in a given position, and then the device produces music tone, or it's irrelevant for this. Okay, so the language I'm going to use to describe, so I'm going to exchange a bit between, let's say, these more physical, more physics motivated pictures. I mean, they are very minimalistic, but okay, like you can see are physical systems in which you perform actions. And then I'm going to use the language of causal networks, which I like a lot. So I'm not inventing this language. This is well established beyond physics. When people study causal inference, no, they use the language I'm telling you about. And basically what people do is you have two variables, no, and they are correlated. You try to explain the causes. So this can be like smoking and having lung cancer. So usually there are correlations between these two variables. And okay, this is smoking and this is having lung cancer. We tend to think that if you smoke, you have cancer. Okay, but of course, by this, okay, we know also that the other possibility is also in principle possible. And if you talk to tobacco companies, they will tell you, oh, there is a variable you didn't observe in your experiment, which is that people sometimes get nervous. And those who are nervous, they tend to smoke and they tend to have cancer. And this explains the correlation between the two variables. Okay. And then you model this by putting an extra variable that you didn't observe in your study, and this is called a hidden variable or latent variable. And I'm going to represent it with squares. Okay. And arrows tell you some of the flow of causation. And as physicists, we always think that this causation is created by some physical carriers that bring the causes from one place to another. It can be matter or it can be energy, photons. Okay. So I think it's a natural language to represent physical experiments. So for instance, if you think about this experiment in which, okay, you have a system and this system prepares particles, and these particles can be in different states depending on which button you press. So here, when you press a button, there is a particle that goes from this device to this device. And here there's another observer who presses a button, and then a particle goes to this device, and this device you collect the two particles and you make a measurement of R results. So everything is expressed by the probability of seeing a result R when you press button X and button Y. This is now the description of the physical experiment. Well, this is the causal network description. Okay, so you have a variable X and Y, and R is causally connected to X and Y. This is simple, everyone can follow what I'm doing. Now, I'm going to talk here, the workshop is called Varieties of Indeterminism. So my notion of indeterminism is going to be quite naive. I'm not a philosopher. So I'm going to take this as randomness. I'm not, so we may have okay, let's see how things go, okay? So if you draw something like this, okay, here you see you have this variable that has no antecedents. So it seems as if there was no cause for it. So it seems to emerge. You may argue that this is random. Okay, I don't think we want to go that far. I don't think people mean that this is random. Okay, so it simply means that if you know this variable, this is enough to understand the causation, what happens here. Okay. Because if you think about it, I mean, people may tell you that there is this model of superdeterminism that was also mentioned, no? In which everything was created at the Big Bang. Okay, this is a hidden variable. We don't have access to it. We simply know that it exists. It's a lambda. Actually, it's a big lambda because it's the Big Bang. And well, everything follows from that. Okay. So, I mean, what is that? This is messy. It is a manifestation of R. Okay, and then, well, even what I'm saying now, it was mentioned today in the morning, it's remember this. And I think this is unfalsifiable, I believe. At least I don't see how I could falsify the existence of this theory. Well, you may even say that there remains a variable with no antecedents in this model, okay? Because, but again, I mean, I guess we are pretty to understand that maybe it's difficult to even pose intellectually. How can it be that there is a, I mean, we are ready to accept maybe there is a variable with no antecedents in our measurement. Okay. But I would say that, okay, this is a possible model. I'm not going to discuss more about it. But I think once we do science, I think at some point we abandon this model because in a way, okay, I think we agree that causes propagate with physical information carriers. Okay, I think this is accepted. Well, I would say that if this big lambda that determines everything, I wouldn't say that it's available everywhere in the universe. So for instance, it determines what I'm doing here. It determines what my kids are doing at home in Barcelona. But I believe even if I had access to all what is happening here, all the variables here, I can still not predict what my kids are doing in Barcelona. Okay, so it's not that lambda travels everywhere in the universe, and since I have it here, I can say what my kids are doing in Barcelona. So somehow I would say that a part of lambda arrives here, but this is enough to describe all what is happening here, but I cannot describe what is happening in Barcelona because some other part of lambda went there. So I haven't thought carefully about these things. I was thinking about these things while coming here. So this is my, at least, I was thinking that the fact that there is a lambda doesn't mean that this lambda is everywhere. Because also, I mean, in terms of information propagation, I see it a bit difficult. But okay, we still think that, I mean, we have some sort of local causality. So if I have to predict of what is happening here, depends on the variables that are here and not on the variables that are in Barcelona. Okay, so I cannot predict what is happening in Barcelona because I don't have access to those variables. But if I had access, maybe I could predict it. Okay, so this is why, in a way, this is my understanding why you can put these variables with no antecedents. Okay, these are the relevant variables that tell you how things are going to propagate in a given moment here. They may have antecedents, but I don't need them to explain the causality for the observed variables. Okay, so another thing I want to say, which I already mentioned, is like causal networks model experiments, but you can also seek experiments as ways of implementing causal networks. Okay, and actually the validity of a network can be falsified. I mean, this is causal inference. So you may have an experiment and you think that this experiment is described by a causal network, But then you see a statistics that is incompatible with the causal network. So you understand that this pattern of causes is not compatible with the experiment. So this is why sometimes you make experiments in which you, I don't know, you take a drug and then you see if this is going to affect something, and then you make the experiment and you falsify the validity of this causal network. Okay, and I think this is going to be important for what I'm going to say. I would tend to say, and this is going to assume, that any causal network is possible in nature. Okay, so you can think of, you design these circles with variables and arrows, and you put arrows. Okay, I mean, I'm not thinking about loops. Okay, so I will have what is called directed acyclic graphs. So, but if you invent whatever you want, there will be an experiment for that. And I think this is, I mean, I can design an experiment in which I may be able to enforce the conditions of the causal network. So I don't see a reason why there exist causal networks that are not possible in nature. Okay, so this, what is important, and this is why you can do causal inference, is that once you impose some network causality constraints in the experiment, this gives you non-relevant constraints on the statistics. Okay, so here I'm representing this. Okay, so there are some hidden variables. I don't have access to them. These can be sources that were prepared in the past or at some point. Okay, and the output A that I observe depends on a previous variable X that I can observe too, and what came from this source. And B depends on Y and lambda and mu, and C depends on Z and mu. Okay, so imagine I have an experiment in which I observe these 6 variables, okay, the ones with the circle, and I assume that the network explaining the correlations are given by this condition, okay? But because of that, I know that the statistics has to obey some conditions, okay? So for instance, if you forget about what C is doing, okay, so you sum over the result, what happens here should be independent of Z. This is sometimes called the no signaling condition. Okay, so if you sum over this, you throw it away. It cannot be that this depends on Z because of this causal network. Okay, this simply follows. You say it just follows because there is no arrow going in that direction. And also, if you trace out what is happening here, and you sum over both results, this P result, okay, what you see in this part is even independent from what you see in this part. This just sort of follows from the network. So clearly, if this condition is violated, this is not the causal network describing these correlations. And of course, I mean, different networks might be compatible with the same statistics. Okay, so if I come back to this situation, let's assume I have some observed correlations that are compatible with these causal patterns. It's of course also compatible with this causal pattern. Okay. You only have to think that this guy, for instance, forgets X. I mean, I cannot tell the difference. Of course, if I add more arrows, this is still possible. But somehow, it's possible, but it's a bit weird, okay? Because we expect that if there is a cause, what happens here depends on what is in the cause. Okay, so there must be some sort of conspiracy in what C does to think that there is a causation created here, but in a way, you don't see this causation at the level of correlations. It's a logical possibility, but I think it's weird, I would say. But it's logically possible, and you will never be falsified. Okay, so it's a bit weird that this goes here, but still the correlations you see between these two guys are inexistent. They are in a product term. Okay. So in classical physics, or what I want to tell you is that nature is not described by deterministic causal models. Okay, and this is nothing but Bell theorem, as we'll see. Okay, which is the similar result in quantum physics. So what are deterministic causal models? Okay, you believe the same as I was doing. Okay, so you have everything is described by causal networks. Causes propagate with physical carriers, and they explain these causes explain correlations. And now what I will impose is that all the functions that determine the outputs given the causes are deterministic. Okay, so if you look at this, if you tell me this is the causal network describing your experiment, then it follows, if I impose that things are deterministic, that the statistics I will see is just, I don't have access to lambda and mu, so I sum over them. And then a deterministic function on here producing A given X and lambda, a deterministic function here producing B given lambda, mu, and Y, and another deterministic function here producing C given mu and Z. So these are deterministic causal models. And I would say, before quantum physics, I would say this is just common sense. Okay, it's very surprising that things don't behave this way in nature. And this is a consequence of Bell scenario. Okay, so what is, does everyone know about Bell scenario? I'm going to explain it, but okay.
How do you know?
In a small workshop, it's nice to answer the questions by the speaker.
I know.
You know, okay. Yeah, I would say.
Yes.
Yes, okay, good. Thank you. But I'm going to spend some time anyway. So what is the Bell scenario? Okay, it's just an experiment in which there is a source that prefers two particles, two systems, and they are sent to two separate locations, which there are two observers, say Alice and Bob, and they make measurements. Okay, so the measurement they make, again, is labeled by X, A, Y, and B. So it's a description in which I don't make any reference to any physical theory. I'm not saying that this is classical physics, quantum physics. It's just, I'm just describing an experiment. Again, I don't make any reference. So this is, again, the scenario. Well, this is the causal network, okay? Well, there is an output that is produced here that depends on a previous input and what came from the source. So you see, it's the same, okay? So I would say that historically people were thinking like, okay, this in Bell's, no, it tells you that you prepare a state of two quantum particles and you make measurements. But again, in the Bell scenario, there is nothing like quantum particles, just particles that came to a place and you made measurements on that. So this is the causal model that explains the experiment. I think you can also put it in the reverse way. Okay? So you want to start with this causal model, and then you try to make an experiment that meets the condition of the causal scenario. Okay, so I think I can start here and say, oh, because of the experiment geometry, this has to be the causal network. Or I can say, I want to achieve this causal network, so I will arrange the experiment in this way to meet the conditions of the causal network. So again, can I be sure that there is no connection here and that this Y is not connected to that one? I can't. Okay, I will try to make conditions so that this is not the case. So how do people avoid this? Well, sometimes people, for those who know better, they tell you, okay, I will arrange things so that these things are space-like separated. So there is no time, not even for light from going to one place to another. I don't think this is, I mean, I know for historical reasons, people like this a lot. I don't find anything super convincing about this. Because if you want to define that this is space-like separated from that one, you have to define the moment in which the event starts and ends. Okay, and if you don't have this timing information, you cannot say that this is space-like separated from this. So somehow you have to put this starting point and end point, which I think is debatable. In my opinion, to think that this is not connected to this, I think there are other solutions that I find more satisfactory that do not require space-like considerations. I think, as some of us know, there is Stefano Pironio, who always advocates that you can take as input of your experiment here the weather forecast or the temperature yesterday, and here you can take the pages of the Geneva phone book. But I don't think the output produced when making a measurement on a particle according to temperature also depends on the Geneva phone book. And I think this is a very much more natural way of enforcing that there is no causal connection between these two variables. So I think for a Bell scenario, what is important is that you somehow, what I was telling you before, okay? So I need to make sure that my experiment is correctly described by this. So I have to find these conditions. And I think there are many ways of giving confidence about the validity of this model, and not necessarily invoking space-like considerations.
Can I just say, I didn't understand. I mean, when you set these things up like you do the way Aspe does it, X and Y are just a binary choice, and you're using really fast optical switches. Really fast optical switches. So that then, yeah, the decision about whether what's going to be measured is made at a space-like separation.
But
I mean, it's really important for the experiment that it be done now.
when did you take this decision? When this was X created?
When the photon hits the optical switch,
But okay, how do you know this?
you just calculate it. You know when you send the photon, you know when it's going to get there.
Yes, but this is just according to your model of theory, which is quantum physics.
You're just setting up really fast optical switches. I'm not sure what,
Yes, I mean, how do you know that this is the correct description? This is a modeling of your experiment. You want to reach conclusions to falsify models. So you want to make a test of quantum physics, let's say, you are using quantum physics to say the validity of your scenario.
the quantum physics isn't playing much of a role in understanding how a fast optical switch works.
Yes, but look, what I'm saying here is that in a Bell scenario, you want to test some theories, okay? Not quantum theory. You want to test some classical models. You don't accept that. So, I mean, if you accept the validity of quantum theory, don't do a Bell test.
Why?
Because according to quantum theory, you violate a Bell inequality.
That's why you do it.
This is why you need to make an experiment. But you need to make an experiment to falsify local models.
Yeah, you're doing it to falsify any local physics.
Yes. So according to local physics, there is nothing like a beam splitter or thing. You want to falsify any classical model, including those that may depart in crazy ways from quantum theory.
Sure.
So according to this classical model, I can give you another description in which this decision was taken many more years before the time in which you decide to make experiment. I know it sounds crazy for a quantum physicist, but when you tell me about a split or a switch, you are using a theory. I can say that I don't believe in your theory. I believe there is another classical theory.
You don't believe that the optical switches are switching the reflective, where the thing will be reflected very.
Of course, I do believe me. But what I'm saying, you don't do a Bell theorem to prove me wrong because I believe in a Bell theorem. So you need it to falsify some crazy, well, crazy or non-crazy models that may be part. I mean, Einstein, when he wrote the APR paper, he said, there is another model with the same predictive power as quantum physics, but with maybe many different principles, okay, many different ways of functioning. And you have to falsify these models. The models that tell you will give you the same statistics, but in possible crazy ways in which the way you generate this input has nothing to do with an optical switch or anything like this. This is just modelization. And you want to reach conclusions without modeling anything.
Maybe we should go on.
Yeah.
But you are using a theory to say that, and I want to reach conclusions that are independent of the theory. So I didn't use any theory at the moment. Okay, so if I believe in a deterministic causal model, then these are the correlations I get. You see, there is something here explaining this output given this input, and the same here. And what is the Bell inequality? These are just conditions I'm not going. Yes, I'm going to derive for all models that satisfy these conditions that follows from the causality and deterministic assignments satisfy. Okay, so what is important, again, maybe this is related to what the previous question, is that there is nothing quantum in a Bell inequality. I never used anything related to quantum in the derivation of Bell inequality. Okay, I'm just saying that if these causality constraints are satisfied and you have deterministic assignments, then this condition follows. So what is a typical example of Bell inequality? This is the simplest, okay? Clauser, Horn, Shimoni, Holt. Clauser, he won the Nobel Prize this year. So it's basically there is a source. The reverse loop. Yes, okay, I have it here. Thank you. Have a source that prepares two particles, and you make two measurements, and you get two outputs. And this A1 is the output produced by this device when you use input one, and this B1 is the device produced by this second device when you make use input one, and what is this is B2 is the output by this device when you use input two, and these outputs are equal to plus and minus one. Okay, so if these are deterministic, these outputs are predetermined, so they have definite values plus and minus one. Okay, and then you can prove that this quantity is bounded by two. This is, I mean, this is very simple mathematics, okay? Because If you take this example, everything is +1. You have +1 times +1 is equal to +1. Plus times 1 plus 1 is equal to +1. +1 minus +1, so it's 2. So we can, I mean, I'm sure you can go to the street and explain this to people with no scientific education, and they will be ready to bet money that these quantities can never be larger than 2. This is very simple mathematics. This is a Bell inequality. So to play this, I think we can play a Bell theorem here without making, we can play a Bell inequality without making again space-like considerations. And actually, I would feel more confident about, for instance, taking Flavio and Nicola. I take the mobile phones. Flavio goes to the ground floor. I take a list of 1 and 2 from Barcelona that they don't know in advance. Nicola, did I say you remain here? Yes, you're a bit older than Flavio. Flavio goes down. So I give them the list of questions with 1 and 2, and they have to say plus and minus 1. If I have their mobile phones and they cannot communicate, I'm sure they will never beat this. And this is, to me, a situation in which the constraints are fairly satisfied without invoking any space-like consideration. Of course, I have to take the mobile phones and make sure that they don't communicate. Okay, so here's now the first time in which quantum physics comes into play. Okay? Because you can violate the inequality. Okay, so there is an experiment in which you prepare a given entangled state and you make some given measurements and you compute the value of the CHSH Bell. You get to further 2. Okay, so what I'm saying is that if Nicola and Flavio have the Bell inequality, they remain here and we have the Bell scenario, and I take the mobile phones, they cannot win the Bell game, even if they agreed in advance and they wrote how to behave in some instructions. Okay, so let's imagine that Flavio and Nicola had a paper in which it's written, okay, if the input is 1, do this, if the input is 2, do this. Okay, even they have this piece of paper in the pocket, they cannot get something larger than 2. But if they had quantum instructions, so if they had this prepared this state in advance, this is a pity that we cannot do this today. But if they had this state in advance, they put this quantum particle in the pocket. They take the questions I prepare in Barcelona. They take the quantum particle out of the pocket. They make a measurement depending on what is written in the piece of paper, and they produce an output depending on the measurement result. They can win this Bell test and get something larger than 2. I think this is really surprising. I think we cannot do this in practice, let's say in our scale, but if we could go to the streets and force people to bet and get their money. Okay, this will be a first application of quantum technologies. I'm sure you will find people willing to bet a lot of money in this. And the only thing you have to do is to have many maximum entangled states in your pockets and make measurements on these particles.
That's why we work on quantum memories.
Yeah, exactly. Yeah. You could store these in the quantum memory. But what I'm saying is that a quantum memory is nothing like this piece of paper in which you wrote instructions that you have read in advance. So it's just the nature of the physical information that varies, and it allows you to either violate or don't violate the inequality. So what is this telling you in terms of causality is that I would say that the description of causal connections in your experiment don't change, okay? So that was the pattern, because I believe this is a description in terms of causes of my experiment, and I was imposing that on top of that I had a deterministic assignments. And what quantum physics tells me is that this is no longer valid. And you have another way of describing the experiment, which is still causal, let's say, okay? Because there is still a quantum cause coming from the source, and another cause coming here, and then the output, in a way, is described by a measurement making on this quantum, this physical information carrier. Okay, so the notion of causality, I would say, is the step, in my view, it's still the same causal network. You only change the nature of the causes coming from the source. Before it was classical information, now it's quantum information. You have some other rules to compute probabilities, but for sure it's not based on deterministic assignments. So this is why we say that quantum physics is not deterministic, because you violate a Bell theorem and then you cannot explain things by causal deterministic assignments. Okay, so this is just maybe a long tree. I don't know if it was clear for non-physicists. For physicists, I was saying many things that they know. Why deterministic? I mean, why the in a way, nature, if we believe in causality, is random. Okay, because there is no way with deterministic assignments that you use 5 other experiments in nature. If you want to respect this causality constraint. So once this is understood, we can study randomness in physical theories, and this is what I'm going to try to do. So in particular, I'm going to do it in quantum theory, because then I think it's clear, and it's one of the main consequences of Bell theorem, that deterministic assignments do not suffice. So now we can try to somehow define randomness operationally and make use of it and even quantify it. Okay. So what is randomness from a, I would say, more operational point of view? Okay, so I have a physical device. The physical device produces some outputs. This is me, the user. So it cannot be that my definition of randomness is I cannot predict what's going on in the experiment. Okay, because this is a poor definition of randomness. If I flip a coin, I cannot predict what is going to be the result. But we believe that this is not randomness. So I will, in my definition of randomness, I would say that things are random if they are unpredictable, not only to me, but any possible user, any possible observer compatible with my theory. Again, I want to describe randomness in a given physical theory, in particular in quantum theory. So this is unpredictable and random, not only if it's random to me, but if it's random to anyone else, in particular a possible enemy that is correlated to my system. Why do I like this definition? I think it's satisfactory both from a fundamental and applied perspective. Well, I think it's difficult to argue that something is random if someone can predict my output. I wouldn't say that it's random. And from an applied perspective, this is useful because if I get something here and I know that it's unpredictable, not only to me, but to everyone, I can use it for practical purposes. Now, if you buy this definition, that randomness exists in classical physics, well, it doesn't, okay? Because all the randomness we have in classical physics, well, this is what I would say. Classical physics is a deterministic assignment. All what happens in my lab is determined by, in a deterministic way, by the initial conditions. Okay, so
that is what is happening in your theory, not in the lab.
Well, in my theory, yes. I'm describing randomness in physical theories. Okay. So the roulette in practice might be random. In principle, within the theory itself. Okay, so there's this quote by Laplace that tells you. Okay. And from a practical perspective, I will spend a bit of time with practical perspective. This is also relevant because, I mean, the problem of randomness also, once you define it, you also want to have ways of certifying that things are random. Okay. And usually what people do is that they verify this by tests. These tests look for the absence of patterns in the sequences that are produced by the possible random number generators. Okay. So do this really certify the presence of randomness? Well, it's known that, I mean, you can never certify the presence of randomness with a finite set of tests. And do they certify a form of quantum randomness? I would say that it's even less clear because classical systems pass this test of randomness. And there is a very clear example of that it's very hard to certify randomness is because if you go to Wikipedia and you look for RANDU, okay, this was a random number generator. Okay, good, yes. Was a random number generator that was used in the 60s. People say that this is random. And then, I don't know, someone had the idea of plotting 3 numbers produced by this random number generator in the XY plane, and a pattern appeared. So these numbers were random until someone had this idea. So this is why I'm saying that you cannot argue that something is random if it looks random to you. Okay, it has to be random to someone else, including the guy who had the idea of putting this into the XY plane. So this is not random for sure. And the second thing why we care about randomness is because, for instance, you can never exclude this type of, you also want really that things are unpredictable to everyone. Okay, I always have this example, which is a bit academic, but okay, imagine you have a virtual casino and you come to me and you want to, well, not to me, you go to Nicolas Gisin, and you want to buy a random number generator. And you know that Nicolas Gisin can get you quantum random number generator. But Nicolas Gisin also likes money, and he knows that you have a virtual casino. So what he does before you come to him, he uses one of his random number generators of very good quality, generates many random numbers. He copies these random numbers into a virtual memory. Into memory, not virtual, into memory. He puts this memory into a box. He paints this box with fancy colors, writes quantum random number generator. He charges you a lot of money for that. You take this random number generator. You ask Nicola, is this quantum random number? And Nicola tells you, yes. You go to your place, you generate random numbers with this machine. You pass a statistical test, you use it for your virtual casino, and then he takes your money. Because what the box generates is random to you, but it's not random to him. So we want to avoid these possibilities. So this is what we want to do. Okay, so it is you, this is Nicola, this is the device, and you wonder whether this is random. And this is not Nicolas Gisin, because Nicolas Gisin knows that you can be sure about randomness, but in the joke, they think that you cannot be sure about randomness. But actually in quantum physics, you can be sure about randomness. And this is because, well, what we ask from Nicola is two devices and perform a Bell test on these devices before running your virtual casino, okay? And because all what I say before, you know for sure that no one can predict the outputs produced in a Bell test because the outputs are not deterministic, because someone could predict them. This would give a deterministic causal model for your experiment, but you know that there is no deterministic causal model for your experiment because you violate the Bell inequality. Okay, so this Bell theorem tells us that nature cannot be described by deterministic causal models, that you can design quantum experiments in which you see this violation, and then you can use the same experiments to produce certifiable quantum randomness. So now you take this, you know that no one, not even Nicolas Gisin, can predict these outputs, and you can use this for your virtual casino in a safe way. Okay, I think I'm not going to say this because it's a bit. Yes, I mean, well, okay, maybe yes. Okay, so you can even make this quantitative. Okay, as a function of the Bell violation, you can see how much randomness there is in your in the outputs of a Bell experiment. Okay, so I went a bit fast. I hope it's good for you. So I come to the conclusion. So what I wanted to tell you is, like, in my opinion, causal networks is a very natural language to describe experiments. And as I say, in a theory independent way. So you can simply say, okay, I believe that in my experiment, there is a device that prepares particles. These particles travel in space-time, and then I make measurements and I get outputs. So I'm not saying that these are classical physics particles, quantum physics particles, just description of experiments in any possible physical theory. And I think this connection between the experiments and the causal networks goes in the two directions, okay? So you can say, like, okay, I believe that these particles are prepared here. One goes to the right, one goes to the left, and then you can, the narrative of your experiment, you can describe with a causal network. And at the same time, you can also give me a causal network, and I can try to enforce, by many different ways, the constraints that somehow give me confidence about the validity of the causal network. And I would even say that I don't see any boundary in preparing causal networks in experiment, okay? So if you tell me, look, you have to do this in which I prepare this, I get these variables here, and this propagates to these different locations and deal with these experiments, I think I should be able to enforce this in an experiment by doing space life or by using potentially uncorrelated sources of information for my experiment. As I was saying, the temperature estimation or the Geneva phone book. Okay, for me, these are clearly uncorrelated sources of random variables. Classical physics respects all these causality constraints, and outputs are produced in a deterministic way. So the outputs in the network are produced in a deterministic way from the antecedents, from the causes. And these models, I mean, they can be as crazy as you want, but they satisfy Bell inequalities. And Bell inequalities are violated in quantum theory, so no causal deterministic theory can explain nature. So we have to accept there is randomness. And once you accept this, you can make use of it. I mean, this is maybe not the conference in which we are going to discuss about uses of randomness, but of course we can also make use of it. And this is something that we also do in my group. And I think this is all what I wanted to say.
Thank you.
We have time for questions.
This is actually based on something that Marina texted me during your talk.
Thank you. Thank you.
I guess, well, yeah, Marina Cortez, who's watching. So well, is there a limit on how much information or can be connected in one of these causal networks? I mean, I think it's arguable that because the universe has a finite age and a finite volume, at least the observable universe has a finite volume, that it's plausible to think that maybe only one, this is something that Marina reminded me, that it's plausible to think that, say, there could be one bit or some number of bits of information generated per Planck volume, per Planck time, or something like that. Was that sort of limit usually seen in quantum random number generation? Right? I mean, that's a very, well, there are a lot of bits being that in principle could be created with all those Planck times and Planck volumes since the beginning of the universe, but I just wonder if those limits play any role for quantum random number generation, or is it, yeah?
Yeah.
Do you have comments on that?
Thank you.
Okay. For the question first, in all what I'm saying, I never impose any limits on the information or the process that takes place in the different locations. Okay, so the only limits I impose are the ones coming from the causality constraints. So for instance, when I consider, and this is the power of Bell's theorem, or what I'm going to say, or what I was saying. Okay, so when you study these causal models, I'm not saying that the information content of what comes here is limited, or that this energy is bounded. I'm not saying that the assignment of the output given the input is P, NP, or whatever. Okay, it can be any. So this is why I'm all this language that I'm using with these boxes or these networks is here independent. I only believe these causal constraints. I know how to model these causal constraints in deterministic causal models. I also know how to. No, okay. Sorry. Yes. So I know how to model them in a classical, in a causal deterministic model. I also know how to model them in a quantum model. But if you think of, you know about quantum physics, I'm not saying that this is a given state of 2 qubits, 2 qubits. It can be even of infinite dimension. Okay. And here it can be any crazy deterministic function you can think of. You are not limited by anything. Okay. So this is why these are limits on the correlations you can get only coming from causality constraint and potential the model you use to produce the outputs given the input. So this is any causal deterministic model will have this form. I'm not saying that this, I'm not putting any other constraint on the function or the energy or whatever. And the same for quantum. This can be any state and you can have any measurement. So it's a limitless model. Of course, you say on top of that, I want to say impose some other constraints that come from a physical motivation. You can also do it, but I didn't use any of those conditions in my reasoning.
Right. Can I follow up? Thank you, Flavio. Thank you, Antonio, and thank you, Mark. This is Marina speaking. Can I follow up on the very useful formulation of Mark, of what I've asked? So I've discussed with Mark that in my opinion, we wanted to bring quantitative limits on all statements that we make together, because we are all coming from very different fields in physics. And from our perspective as cosmologists, we have very well-defined limits on the length of any undetermined number, because there's a finite age of the universe. And if we want to specify an undetermined number as dictated by in the lab or in experiment, that undetermined number in the real world can only have so many digits or bits, because there's only so many units of time that have passed since the Big Bang. And so, because we come from so many different disciplines, we can bring together limits, objective and quantitative, outside of theory, but what are the limits that the real world has for us? And in this case, I guess, of course, I'm assuming that the Big Bang did really exist, that it lies outside of theory in the real world. That's also an option for debate. But I wonder, given that the universe has a finite time of life, how can we merge that with a statement that we make on how undetermined a quantity is of information?
Yeah, everything is finite.
Yes, no, I don't think this, okay, of course, it's a nice problem, what you're saying. I don't think it's of relevance, say for, it sounds too strong what I'm saying. So I don't think it applies to what I'm saying, okay? Because, so in Bell theorem, you want to falsify these causal deterministic models. So for that, since you want to falsify all of them, you should not put any limit on them. So you play this trick, okay? So you only have a causal deterministic model that has to produce, if you remember, as Nicolas said, I will do it here in this Bell scenario, you see. So this can be as crazy as you want, but it has to produce two outputs. Okay, and you perform two actions. So everything is finite, but you can think that this can be, I don't know, something really, really crazy. And the function producing the output, even the input, what came from the source, I don't put any bounds on that. And then whatever it is, you always have this bound equal to 2. And now you want to falsify these theories, and you do it with a very simple quantum experiment. And for all our purposes, it's enough that this quantum experiment produce a value with this concrete realization. Of course, now you may wonder about, okay, what are the ultimate limits in quantum physics about this experiment? This is a relevant question, which actually in this case is also quite simple. It's really given by this. So I think if I don't need infinite precision to violate a Bell inequality. I only need to have two outputs and calculate the statistics. Of course, I will have finite precision in statistics. Okay, like in an experiment, you need to get a value larger than 2, and you will see a value that starts being larger than 2 with a mean and a variance, and you will have, I don't know, sigmas of deviation and things like this. So you never have perfect confidence. I don't see any. I mean, the considerations you are telling about, I don't see how they could play a role in what I'm discussing.
I think time's up.
Yeah.
Thank you.
Yes, so I understand what you're saying, and that makes sense. So my question is more of operating when we are discussing all of these topics, that we can be defining very well what we mean by undetermined and determined. And your statement on we don't need infinite precision to violate Bell's inequality it answers the question in a very positive way. So that's
yes. So my only statement about determinism is that causal deterministic models don't reproduce experimental predictions. Because I think this is just a summary of my talk.
yes, exactly. So that's very helpful.